we shall listen to Andrea Gruber from CDN, and he will talk about DNS of flame propagation in several boundary layers.
So hello. This talk was scheduled for Friday, but because of some last-minute work I have to do for syntax, I couldn't do that on Friday. So I will talk about this today. The same presentation, well, a modified version of this presentation was shown at the end of the turbulent boundary layer program last month. Now I will show some more chemistry than I did at that time. And at the same time I will give some more information about boundary layer structures that I did not in that occasion because I had less time. So the people I have worked with are Evat from, he was at Sandia before, now he's in Sydney. Ramana is now at Oak Ridge, and Jackie and Ray at Sandia. So what we see here is a channel flow with some turbulence visualized by the by lambda 2. And how this turbulence interacts with the flame shown by progress variable isosurface. Well, at first consideration, we see the effect, as Jim was showing us, the effect of the flame on the turbulence. It basically wipes it out, in this case. It is I will come back to that, but this is a channel flow as one of the first one made by Kim and Moser with DNS. So it is not very high Reynolds number, but still it's a fully turbulent case, and there is quite a lot of shaking, especially near the wall. So the motivation for this is that, well, I will quickly go through this. We have many industrial applications for combustion in confined volumes, and these sometimes bring problems with flame towards the wall. One example that I show here is a gas turbine burner. This is the EV burner from Alstom. It's double cone. But flame wall interaction is important also for automobile engine application and so on. I believe that the models that we have, the ADC flamelet, thickness flamelet model, they are all very bad when it comes to boundary layers. I mean, they are developed. This one is developed for isotropic high Reynolds number turbulence. So that I know will fail because I tested this case against the DNS, and it does a very bad job. About these others, I'm not so sure, but given the assumption that these other models and many other models do, I don't believe they will perform much better. So what we see here is a lead premix pre-vaporized burner for liquid fuel sprayed from the middle, or gaseous fuel injected from small holes in the premixer. Why I show you this? Yes, because what happens, and we do not want to happen, but sometimes there is the flame flashing back into the premixer. And there are several mechanisms for flame flashback. I will not go through all of them, but one of the mechanisms that brings the flame inside here is that the flame creeps along the boundary layer in the low velocity region, and this is why we want to study some more this turbulent flame wall interaction. Another thing that I've been doing lately is simulation of a jetting crossflow. I have the slides here, but I don't think I will have time today, so we can take it another time. The reason for this jetting crossflow simulation is that because if the flame comes in here somehow because of some transient in the engine, and it comes very close to this gas ejection holes, one wants to design this fuel injection point so that when the transient in the flow is gone, so the compressor surge is stopped and the flow is back to normal, the flame is blown out of here. So the flame does not anchor at the fuel injection point. So we want kind of no flame holding at the fuel injectors for that gives them intrinsic flashback safety. I hope this was clearly explained here. If not, just ask. So I have been studying in the last years two phenomena: the boundary layer flame propagation. So this is relative to the flame creeping along the wall in the boundary layer, and also fuel injector and flame anchoring. So kind of jetting cross-flow configuration. So therefore we have this case that I will talk about today, and then we have this other case, which is a jet in a cross-flow. I have the slide, but we'll see how long time, how far we come. This case we have a pre-mixed situation. The fuel and air are mixed here, while here we have a non-pre-mixed flame.
Is the flange stabilized?
Yes, I come back to that. So all cases are run at Oak Ridge using the code named S3D. It's a Sandia code. So the mathematical model is the compressible form of the Navier-Stokes equation, the energy equation, and the transport of species. The source term are modeled with the usual source term approximation with reaction rate in this reaction given by the mechanism. So the chemical mechanism, these constants BA and EA, come from this mechanism. Or hydrogen air. Yes?
New dash and new dash twice. It is what it is. How to say?
Yeah, the stoichiometric coefficient.
But what? It is direct reaction and.
Yes. Exactly.
Am I understand correct? It should be true, not far from equilibrium. Because, if I remember correctly, this is you've got W. This WI is the same. Is it
Yes.
true?
I don't understand. This does not assume anything about equilibrium.
Have you taken into account Brownian diffusion?
Hmm?
Have you taken into account Brownian diffusion? Yeah.
Well, the
equation.
what do you mean?
Brownian diffusion, that's just
No, molecular
diffusion.
diffusion. Molecular diffusion. Molecular.
Yes,
Yeah.
yes, it is. About the numerics, it's the code uses 8-order explicit centered finite difference and 3rd-order on the boundaries, and the temporal high-order integrator. So it's I would say high-order code. The case is defined as follows. Now I come to the flame anchor that you asked about. So we have the upper wall, the lower wall, channel, span-wise is cyclic. So the approaching turbulent flow is hydrogen air at phi 1.5. This is the Reynolds number for the case, and this is the unburned mixture temperature. So the inflow boundary condition on this plane is given by another auxiliary DNS. So it's a parallel, completely separated simulation that I use only to generate the inflow here. Because there is no way to generate synthetical turbulence that is realistic. Yes.
When you use the Gillen's ratio.
Yes,
that was also my
yes,
question.
yes.
Yeah.
Because, okay, for gas turbine this is not the relevant, I would say. But this case was run 2 years ago, and the machines were much slower. So this is a merely a practical point of view. So because with the higher equivalence ratio, we have higher flame speed, and that means that we can blow the channel faster and get statistics at a lower cost. So it's a merely practical reason. I would have liked to use 0.5, but we couldn't afford it at that time. At the same time, I mean, we are studying the interaction of the flame with the wall, and I don't see how this fact that we want to study would be changed dramatically by the equivalence ratio.
So preferential diffusion.
Yes, yes. But, well, it's taken into account, and we know that there is a difference between rich and lean. And so the isothermal non-slip walls are periodic in this direction. The anchor is created by a kind of numerical hot rod. So I impose burnt and conditions and high temperature in this. So this stabilizes the flame. The computational grid is relatively small at these days, 25 million nodes. The computational domain H is the half channel width. The resolution is 32 micron. Now, with this resolution, at this condition, the laminar flame is resolved with, depending on how you count the flame thickness, but it's resolved with looking at, for example, the reaction rate of the fuel. There are 16 points through the reaction rate of the fuel. Okay, the reaction rate of the radicals, the ugliest one, are about 8 points. Okay. So this is for okay. What I said was about this, not about this. Okay, because the grid is stretched, and at the center line has a lower resolution. At the same time, at the center line, I have an anchor which kind of messes it up anyway, a little bit. So the statistics, the flame is slightly unresolved in this region, but we are interested in the flame interaction, so we do not care so much there. Yes?
Did you impose boundary condition at the flame anchoring wires?
Yes.
Or is it calculated automatically, flame stabilization?
Well, I impose in this rod, I imposed the product composition as it is burnt, okay? And the high temperature. So I impose burnt condition at that point, and I smooth this towards the solution. Okay, so this is a kind of boundary condition actually, that I smooth, that I merge to the solution. It is the method that we have used. You have to be very careful with high order stencils because you would get some noise if you don't do it carefully. But we have done this, and it is not noisy.
How about the velocity field?
Okay?
How about the velocity field? That's the question, I think.
Yeah.
The velocity field of
Velocity field around the wall.
If it's
on
a
the
chemical
road.
condition,
No, I
velocity
did not impose any velocity.
Okay.
So it's only on
It's
the
not like
species, only species and temperature.
So there's
It's
no
not like a
boundary
graph
condition.
No.
It's not a string.
Well, what happens here automatically by itself that when I put a very hot, very high temperature here, you will have an acceleration because of the density.
It's like an ignition, constant ignition.
Yes, it's kind of constant ignition. You can picture yourself having a powerful laser through this domain. Okay, it would have the same effect. Okay. So about urban boundary layers, I don't know how familiar you are with this method. I mentioned this because it's relevant for what comes later. But you know, this is what we usually look at, and these are the three-dimensional structure. And we had last week here, Fatri Hussein. I have seen, I always put in this presentation his works, and I think they are very nice. So in this case, he was commenting that the current structure is a connected large-scale turbulent fluid mass with phase-correlated vorticity over its spatial extent. These long sausages here. The flow visualization. So these things, flow visualization, presents excessive information but very little hard data, and anemometer data. So this thing gives some hard data but very limited flow physics. I think that one should look at both of them to understand what's going on. It does not, I mean, when you make a model, when you make, like the EDC model is based on you know, K, epsilon, and some constant, and then you get a profile of U, you get a profile of K, you get a profile of epsilon, and you put this into your model and hope that it will take into account frame wall interaction. It doesn't. You have to understand what's going on at the detail
Yield
level.
structures.
Huh?
You mean you should take into account yield structures
Yes.
too?
Okay, so Kim and others have estimated this streamwise structural size, about 30 wall units. Others have estimated the turnover time. So this has been going on for many years. And who else? Jimenez, also, he was here also last week or 2 weeks ago. He estimated the length of this. So I'm reporting all this because these numbers will come later into the analysis. Also, Hussein again estimated the convective velocity of this structure to be a little larger than half of the centerline speed of the channel. Here we see the flow is into the plane. We see examples of these structures. So we have these vortexes here, and of the low speed ejection, as we call it. So between two counter-rotating vortexes, you have ejection of low speed fuel towards the center line. So low speed fuel from the boundary layer comes into the higher speed fluid here. And then we have the high speed sweeps. So faster flowing fluid is pushed by the vortexes towards the wall. So we have this alternance of high and low speed streaks. They can be pictured like this. So the ejections are these lifted surfaces, and they have typical length and spacing. This is from one of the simulations. You can see the ejections. So if you can do this typical spacing and bring it to millimeters, for my case, then we have for this viscous length, the typical length of the structure is about 6 millimeters, and the typical spacing 1.6 millimeters. Why I mention this? Because we will see that the heat flux towards the wall, so the induced by the flame, depends, I mean, acts on these scales, and also on some time scales. And when they are so small, perhaps they don't mean anything. But when the Reynolds number changes, and some of the guys who were here, Ivan Marusik from Australia, he showed some superstructures that form at much larger scales. They can have an effect that is on the wall, for example. It can induce thermal stresses that are not taken into account in any model. Okay?
Reynolds, turbulence Reynolds, which based on the NG contained scale of turbulence. What does it mean, Reynolds turbulence?
Yeah, in this case, in the channel flow, that is the Reynolds number based on the tau. Okay, it's 180. If you based on the velocity, it's 3002, I think. So it's.
So you mean frequency, velocity, you star, and what scale when you calculate Reynolds?
The viscous scale. So it's 16 micron. You see this? This one. It's the viscous scale.
Yeah, but this is
usually
it's turbulent this scale, you mean?
it's the I don't
It's
know
the same
what.
simulation scheme. So
Yeah.
it is Linus Tower it is. Based on the friction velocity.
Yes, right.
And then the half of the channel height and the
I
viscosity.
just said channel height, you mean this?
Half of the channel height.
So again, here we see a simulation from Boole and Moyne of a boundary layer, and we can see all these A-pins and structures of the boundary layer. So this is an open boundary layer. The structure I'm talking about, you cannot really see them here, but they are small sausages-like vortices that lie down here. Okay, they are not these ones. These are very big compared to.
What is this color means?
It's the okay. The structures are visualized by the lambda 2 method, but the color is the distance from the wall. So the red tops emits those that are furthest away, and then the closer to the wall you become blue.
Look
By the way, there's quite a lot of discussions about this, so
Yes.
this is not what you really see in a turbine boundary layer if the lines number is high enough.
Well, yeah. I mean, this was just a result to show that these things have different scales. Okay, so you have large scale things and small scale things near the wall, and in the channel flow, it will be something different again, because you will have the influence of the. I mean, the flow will be completely turbulent. Here you will have a irrotational fluid on the top of this. Okay, so this is the channel flow that I did myself with the passive scalar. And here you see, so the wall is at 300 Kelvin, and the flow center, I mean the bulk flow is at 750 Kelvin. And you see an isosurface of the green one is temperature at 700 Kelvin. How it is changed by these structures. So in case of the passive scalar, obviously these vortexes, they take the passive scalar away from the wall in the ejections and close to the wall in the sweeps. So this phenomena is very well known, and it acts on the passive scalars too, obviously, and it has been studied for a long time on the passive scalars. But the flame is not a passive scalar, and there was very little in the literature about flame propagation in boundary layers.
You mean concentration of passive scalar particles in the vicinity of...
Now this is not particles, this is
not
temperature.
temperature.
So you see that this is a zoom in this region. You see that the vortex bring cold fluid up from the wall, and here it brings warm fluid closer to the wall.
What does this color mean?
Yeah, well, okay. The green is the surface, so the passive scalar surface, temperature. While the blue and red, they are vorticity, X vorticity. So these different colors are counter-rotating vortexes, actually. And you see also, well, it's not so easy to see, but if you look at the vectors that I plotted, you can see the rotation.
Where is the temperature is concentrated? I don't understand.
Yes?
This practically planes. What temperature? Is the temperature of the wall?
No. The wall is at 300 Kelvin, fixed, it cannot change. The center line temperature that we don't see, I mean, it's 750, and this surface, the green surface, is 700 Kelvin. So it is in the boundary layer. There is a thermal boundary layer from 300 to 750, and you see that the passive scalar is not a flat surface, but it is
blue color. It's what temperature?
vorticity.
It's vorticity. It's not temperature.
The green is the temperature. The blue and the red, they are vorticity in different directions.
Okay, now.
So temperature is concentrated between the two voltages.
Yeah.
Is correct? Okay.
By the way, this was after the flame then.
Now this is no flame.
Okay.
It's a channel flow without any flame, just to show the effect of the on the passive scalar. Here you can see how the simulation was started. These blobs here are here because I start the simulation from isotropic turbulence, so which is plainly drawn for the channel, and then you will see these sausages develop. Okay, and this plane is the velocity in the stringwise direction. Okay, and you will see a black line here that will appear. It's the temperature at 700 Kelvin. So you will see how these sausages will change, obviously, the velocity plane, but they will also change the passive scalar contour.
What's the typical Mach number in this calculation?
Not very high. 0.2, 0.1, 0.2. You see now they are formed, and well, there are many, but you can see that the surface, the black line, which is the 700 limit, is modified and pushed away on some places and pushed towards the wall in other places. So these vortexes, they are embedded in the solution of the Navier-Stokes equation. They are always there. Here you can see it very well. This vortex has brought the scalar up away from the wall here and toward the wall here. Okay, then we put the flame there, and again we concentrate on what happens at the wall. Okay, so again this is the anchor and the flame, and you see that the turbulence is wiped out by the density, by the viscosity increase. Here we see yet another figure of the flame. This 3D figure shows that, okay, the surface is progress variable 0.7, so it's kind of late. And in the center line there is not so much wrinkling, because the turbulence in the center line is not so strong as it is near the wall. So the wrinkling is very high here. You see there is a lot of unsteadiness, and but here not so much.
What is the ratio of brim with laminar scale velocity? The center. It's about
okay.
about 1.
Okay, this laminar speed I showed in the
Yes, I remember.
13 meters per second.
So it's
Very high, because this is preheated, and hydrogen has the top at 1.5 phi equivalence ratio. So it's very high velocity. The fluctuations here, the center line is 80 meters per
So
second.
it's a left laminar flame here at the center.
At the center, yes. But here it's very turbulent. So, yeah, the flame is strongly wrinkly. Another thing that you can observe, this is the average field, okay? And you can see that the flame brush, this is represented by the progress variable between 5 and 95% of the reaction, thickens toward the wall. Now, this thickening can be generated by two things, I believe. One is the fact that the flame oscillates more, spatially, so that the average field would look thicker. The other thing is that the size of the turbulent eddies here, from here to there, become smaller. So we may be in a flamelet regime here, but in a more diffuse flame and distributed combustion regime near here, where the eddies are so small that they are very strong. There is, in fact, another difference compared to many other studies is that in this case it's not decaying turbulence. Okay, many other cases, as Jim's case earlier on, and other DNS studies, they study decaying turbulence. This is not decaying. The turbulence is being generated at the wall by this shear, and so these eddies are very strong. They have well, at least they are not decaying towards the flame.
But you can compare. You have all information.
Yes, yes.
Someone's sickness is
Yes.
Well, one question.
Yes.
If you say that your ADs are small,
Yes.
then you should expect to see some local quenching behavior.
Well, quenching, there is quenching because the
That's due
flame,
to wall.
because of the wall.
Yeah.
But you mean because of the flame being torn apart?
Because of the small ADs.
Yeah. Well, I don't think this is turbulent enough to see that. Perhaps at higher Reynolds numbers we would see that. But what we observe then is that if you take the gradient of the progress variable, you can get an indication of the flame thickness, because the higher the gradient, the thinner the flame. So we did the PDF of this, and so this is the laminar flame thickness or gradient of the progress variable, and you see that the turbulent flame is mostly in this region, but when it comes to the wall, the PDF is skewed toward other values of the gradient. So the gradient becomes lower, so the flame gets thicker.
It was three gradient. It's not just one component of gradient. It was three gradient. Three components.
Yes, yes, yes. So this is an indication that the flame is getting thicker. It's not just the fluctuation of a thin flame that creates the brush, but the flame is in fact getting thicker. And this, again, can be due to smaller turbulence or the heat loss, because there is a heat loss toward the wall. The reaction rate, we see it stops. The flame, I mean, there is no reaction of fuel at the wall. So this is what is called the quenching distance, this little gap between the, yes?
What boundary condition will you use on the wall for the species?
Zero gradient. So the wall is non-reactive. This is an assumption. We know that for wall temperature above a certain limit, there is reaction at the wall. The wall will, depending on its material, it will absorb H radical, and they have an impact, obviously. But this is a limiting case. This was the first test. It's a limiting case. Right now, we are working on implementing reactive wall boundary conditions, and this is not easy.
So do you allow the gradient to exist around the wall?
Yes.
So only the normal gradient.
Yeah, it's only the normal gradient.
Do you have this radical sink mechanism in the reaction?
Radical?
Radical wall interaction mechanism. Is that in your reaction mechanism?
No. The mechanism is the homogeneous chemistry. I mean, it's non-heterogeneous reaction. No. So it's only gas phase.
Then how this radical disappears to the wall?
No, they don't. I mean, in this model, there is no disappearance of radical at the wall, but they would be there in reality. For a wall, I mean, it depends what the wall is. Okay, so this is a limiting case of no reaction at the wall. But if you make the wall of steel, you will have H protons that go into the wall. If you have the wall of ceramics, probably not. So it depends what you use as a material. And we couldn't care at this point about this, so we did a limiting case. And now we are working on more sophisticated boundary conditions.
So the quenching is purely due to low temperatures?
Yes. Yes. Yes.
As I understand correctly, the product of this reaction is water, right?
Well, not only,
No,
but mostly. Yes.
Mostly. No, in your model, I would like to ask.
Well, you saw the whole mechanism. It will take some time to compare. So there are some reactions. You see this.
You have to take into account all these mechanisms.
Yes.
Mm-hmm.
So you see these that have 0 here. These 4 reactions. It's, number 6, 7, 8, 9. They have 0 activation energy, so they don't care about the temperature, basically. They happen even in low temperature. And what do? They recombine radicals to heavier species, like take the number 8. So these are 2 radicals, OH and H, that with the help of the third body recombine to water. So this reaction will have a lot to say at the wall, because basically it doesn't care about temperature, and it will have a heat release because it's isothermic. You combine 2 fast things into slower things. So if you don't take into account this and do one step, you don't see the wall heat flux that I will show you later. Now, let's go forward. Okay, this is the SD, so the flame displacement speed, and is normalized by the laminar speed. We see that in the channel center line, the displacement speed and the laminar speed are comparable, and this is reasonable. But as we go towards the wall, there is a drop. But this does not go to 0, and we still haven't really. I mean, this SD has 3 components, and one of them is given by the reaction, and the reaction is 0. But the other 2 components, obviously, are not 0, since this is not 0. So the fact that this kind of model of the flame displacement speed, this behavior has to be taken into account in the model, and it's not. I don't see it as a very easy thing to do. Yes.
I'm confused. You said that the reactions go to 0.
Yes.
But you just said that some reactions does not do that.
Yes.
So what do you mean when you say the reaction?
Well, the fuel reaction. What I showed.
What consumption of fuel, basically?
Yes.
That's the what
Yes.
you mean.
So when you calculate SD, you calculate heat fluxes, just to find SD.
Well,
If the no reaction rate,
yes.
you
Well, there is a curvature term, and there is a diffusive term. So it's those 2 terms that.
Yes, but it's not.
Well, okay. It's not real. I agree with you, but models use this SD.
Yes, I understand that.
and what do they do? I don't know.
I agree with you.
Yes.
How SD was defined?
As usual.
As you these 3 terms, it has 3 terms.
Yeah.
One reaction term, one curvature term, and one diffusive term.
You use isosurface of concentration?
Of progress variable,
Yeah.
so of a certain progress variable, how it moves in time.
Just preheating.
So here we see the effect of so this is for this line is for the progress variable 0.1, so it's very early in the reaction, and you see that the Kolmogorov length scale compared to the viscous scale, it's well, this is a usual behavior. Okay, this bump, it's interesting. I think I have another. Well, I have it for the time scale of Kolmogorov, but let's look at evolution with the flame. So for higher progress variable, you get this increasingly high bump, and here even more. So this is telling us that since this Kolmogorov length scale is computed in the usual way, yes, so we have a kind of, well, at a very close to the wall, we have a place where something is going on. We are not sure really what it is. Probably it's effect of the acceleration, because there is, in this gap between the flame and the wall, there is a kind of acceleration of the flow.
Delta nu is the thickness of flame or what? Delta nu
No, it's the viscous length scale.
is a viscous length scale, but
Yeah,
Kolmogorov
it-
says it's also a viscous length scale. It's the same.
Well,
Reynolds number equals unity at the
Of the wall. The viscous length scale at the wall.
At the wall, I see.
So you see, this is the same. So this is the normalized, the Kolmogorov length scale normalized by the Kolmogorov time scale normalized by the wall time scale. Okay, and from this guy, and you see that this is usual behavior in a channel. So obviously in a channel flow we don't have a one Kolmogorov length scale everywhere, but it changes, no, because of the different scales. And this is for the flame case. You see that there is this bump that is increased. The scale is mostly the same. We arrive at 14, and this is 12 times the viscous scale. But the viscous, whatever you want to call it, the channel flow scale.
And how do you do this condition of averaging? So you follow the
Well, I take these numbers only on the surface, that is 0.1.
in each point,
Yeah.
and not statistics.
No, not in each point. Because this surface, the C.1, moves.
Yes, I understand.
So you move, I mean, you collect the statistics only on this surface.
And how many events?
Or many. More than 200. I don't remember, but many. Now, after some discussion on the effect on the flame, I come to the quenching. And this is laminar flame. So you see, for a laminar flame propagating towards the wall, you have a certain heat release. When the flame quenches at the wall, you have a tenfold increase in the heat release. And this is because of the radical recombination reaction that I mentioned before. Okay? So this is has been observed from before in laminar flame. And if you look at which reactions contribute to this, number 8. So you remember those that was the reaction that was giving water from OH and H has half of the heat release. So it's very important to have these reactions accounted for. So what we did then was to estimate the wall heat flux along the channel, and we found that the peak was at a certain distance from the inlet. So at 183 and eventually inlet. So this is the line of the maximum. This dashed line is the maximum wall heat flux line, and this is the instantaneous wall heat flux. These colors, look at the scale here. It's megawatt per square meter. So you have large variation of the order of 2 megawatts per square meter in the wall heat flux. This, for this case, at this low Reynolds number and small structures, they are on a length scale that is, well, 1 millimeter, and on a time scale that is very small, 1 millisecond. But for higher Reynolds number, where you have large superstructures, you will have larger length scale and larger time scales. So this can crack things. And it's not included in any thermal paint analysis of any kind. This is unsteady wall heat flux. The thermal paint is only average. Yes.
Just comment. This phenomenon has been observed in engines.
Yes.
It's very typical that they have a changeable fluxes within small distance. A lot. So,
Well, there is a difference. Well, I'm not sure which engine you're talking about, but if you have a combustor which has a flame that comes close to a wall, okay, or you have even the passive scalar transport, so high temperature of the flue gases, and they induce this kind of variations, they will have a preferential direction. I mean, these streaks, they look like this, okay? So you will have these changes that move in time and in space, but they will have this preferential direction. So, I mean, the thermal stress will be kind of a crack appearing this direction. It's not probably the same in an internal combustion engine where you have more of well, not such anisotropy.
it could be.
It could be. Okay?
Is the maximum, the distance of the maximum heat flux?
Yes.
Is that the place where the flame come and hits the wall?
What do you mean? This
No,
line?
No, the one before.
Yes.
The dotted line.
Yes.
Is that the region or the place where the flame come and hit the wall?
Yeah, more or less. Yeah, the flame, you know, it flaps, and you see that these wall-lit flux colors are actually a marker of the flame in this instant. So this is the location of the maximum average wall-lit flux. So it is, the flame is flapping back and forth here, and yeah, this line is sampled on this dashed line. So this gradient are.
So this scale is compatible with the scale of structures.
Yes.
It's exactly.
Well, very close. Yeah. So here is an animation. Oops. Sorry. So you see the white lines are the omega y vorticity, so the wall normal vorticity that marks the streaks, these structures, at y plus 5, so a little bit above the wall, while this is the wall-lit flux. And you see that I will start it again. That they induce. Oops. Okay. Look at this. This is the pair. So it's pushing the flame towards the wall here, and you will see that this will grow and become red, and then become blue again. And this happens all the time. Oops. Okay, so this is the time sample along this line for the lower and upper wall. So we did the spectral analysis of this. And so this is the spatial, the solid line is the spatial spectrum, and this is the temporal spectrum. And so basically, you can see that the top here, this is at 1 over 100, 1 over 100, yes? And this is the average spacing of the structure. So it's very accurate that these structures have something to do with the fluctuation of the wall-lit flux. It is not a proof, but it is a good indication of this. While the temporal spectrum is correlated to a kind of large scale, and there is this plateau between t plus 10 and 30, and so if you assume that the streamwise vortex is between 300 and 600 long, and it has kind of passage time, and 16 is the turnover time as proposed by Jimenez. We have that T26 is a typical streamwise structure flame passage time. So in a dimensional unit, how long time this structure takes to go through the flame. And this is, well correlated to this maximum in the time spectrum. So we have proposed this, as mentioned to you, we have proposed this flame propagation mechanism. So we have the ejection and the sweep. The sweep brings the flame towards the wall, and the ejection away from it. Well, this is probably what's happening. Last 3 slides, I have this collaboration with TUM in Minecraft, where they are simulating a diffuser. And this is a channel flow with expanding bottom side, so that the flame, which is here, it's triggered to propagate upstream, but then encounters higher and higher velocities, and then it stops here, and it flaps back and forth, so you can do some statistics on this. And well, this is ongoing, and we haven't received so many results yet, but this is a picture of the flame going upstream, and this is from the top. This is OH chemiluminescence, and we see that, well, perhaps not from this picture, but we have observed quite clear spikes in the direction of flame propagation that could be related to the streamwise vortexes. We are not sure yet. We cannot. We don't have enough resolution, enough statistics to do this, but that's what we are planning to do.
And what is the amplitude of this fluctuation? The order.
Which fluctuation?
The flying.
Of this?
Yes.
Of this one?
Yes.
I don't know.
Back and forth. What is the amplitude?
Of this flame?
Yes.
To be honest, I don't know. I mean, I know that they managed to stabilize the flame so that it does not go upstream, and this is already difficult with hydrogen, but it will move, yes. But I'm not sure. I mean, this is not something that I'm doing. I just showed that we are doing also this experimentally.
Is it acoustic or not?
No,
Maybe.
no. Well, I mean, some sound there is some sound. Yeah.
Acoustic, yes.
Maybe they have a boundary layer separation there?
They depends. Sometimes, you know, another interesting thing that happens in this configuration is that originally flame starts from the bottom and goes up, but sometimes, because of an instability in the flow, it changes and goes up, and the flow and the cold flow goes down. So it's, I think it's due to some kind of hydrodynamic instability between the flame and the cold flow. That in this situation, the cold flow is pressed upstream and is sucked in by the flame where it's relevant. I don't know. They have been observing some strange things in this configuration. It's not easy to study. It's not, and in any case, they would not have very good resolution here to study the flame front. So this is why the DNS is a good tool.
Is it online? Side line?
Yes. Yeah, because the chemiluminescence is integrated. So, I mean, I don't know how much we will understand from this, but I think it's important to try it. So, well, this I already said. So, basically, it's a summary, and what we are planning to do, perhaps it's more interesting, is to simulate a planar flame. So now we have a V flame. The V flame is very good because it's stationary, so we can make some good statistics. But due to the geometry of it, it's possible that it has some influence on the boundary layer before the boundary layer actually reaches the flame. While if you have a normal, I mean a flame propagating normally to the wall, well, not normally to the wall, but a flame surface normal to the wall, then we would not suffer this. At the same time, not anchoring the flame, it will be very steady and moving back and forth. And well, we are trying anyway. So another thing is that we are trying to do this at higher pressure. This is because the radical recombination reactions, those that induce a very high wall heat flux, they are pressure dependent through the N, the third body. So to see the effect of pressure on that is the next step. Okay, that was all I think. Yeah, okay, this I also mentioned, the fact that the high Reynolds number involves superstructure, and Ivan was here last week and talked about that.
And what's the physics of superstructures?
Mm-hmm.
A little bit, what is the superstructures? What is the physics of superstructures?
Well, as far as I understand, it's quite new, this superstructure thing. But as far as I understand, they have been observed experimentally, and they represent kind of large parents of these small streamwise vortexes that are on the very close to the wall. They are a bit further away from the wall, but they are very strong, and they act on much larger time scale.
Is it not Göttler stability? Göttler.
I don't know. But okay, this is I'm correcting the proof, so this will come out soon. Any questions?
I have the question concerning your calculation of the influence of small vortices on the thickness of flame.
On the thickness
Yes.
of flame, yes.
Because I don't understand. You can compare the thickness of the thermal thickness of the flame
Yes.
with a, I don't know, with a small scale vortices nearby a region of wall. Why you
Yes.
didn't do this calculation?
Well, yeah, I mean, a good time scale, a good length scale at the wall is the viscous length scale. Okay? So you can think that when the vortex, when they are created very close to the wall, they have comparable lengths with this. You saw that this vortex had the diameter of 30 wall units. So that means 30 times the viscous length scale. Okay? So we, in a sense, we have the comparison.
Thermal thickness. What is the ratio of thermal thickness?
Well, you saw the figure. Now, I have the jet, but I don't think I have time for that. Where is it? Here. Well, this is a kind of flame thickness, huh? The average one.
Before, not the average.
Ah, okay,
Not
on
average,
instantaneous. Yeah, okay, I understand. I understand what you mean. No, I haven't done this, but I mean, it's possible to do. But I mean,
in this case, your discussion about the influence of small vortices is not convincing because this thickening of flame.
I don't know. I'm not saying that I've said that I don't know why the flame gets
Because
thick,
maybe
thicker.
due to heat force.
Absolutely, absolutely. I said that I don't know.
So
I said that I don't
you-
know. It could be the fact that the flame is entrained by small vortices. It could be by the heat loss. It could be by the fact that the flame moves more.
But why you didn't compare the thermal thickness with the small vortices?
Well, in the instantaneous sense, it's not so easy. You can do it on an average sense, but it's not what you want. In the instantaneous sense, it's not so easy.
But you can calculate instantaneously.
Yeah, but then for what vortex? I mean, you can use the viscous scale and multiply by 30, but it's not sure that what you are looking instantaneously is so big. I mean, either you do a length scale analysis on general terms, or you do an instantaneous analysis on the flame surface, how it looks at time t equal something. But then you have to find a way to define all these small vortexes at that time. And it's not obvious to me how to do that.
And when you perform the calculation, it's not clear. You can't analyze really the relation between the vertices and the thermal settings. It's possible to see or not?
Yeah, I mean, we can look at 200 pictures and see if we learn something, but
It's not clear.
well, it's possible. I'm not sure that we will learn so much. I don't know. Perhaps.
I was thinking that this thickening must be due to this fluctuation, not due to the thickening of the local structure. Because the thickening of the local structure is anyway an order of magnitude smaller than this mean. Am I right?
I don't know. This, oops, no, please. That picture, the one from of the PDF, seems to suggest that the flame itself. Why? Okay. I cannot point when. Really? I mean, this is the PDF taken at 0.7, the progress variable, conditional on the progress variable 0.7, and it seems that for when the flame gets closer to the wall, it gets thicker.
And the PDF is more it's like ink.
Yeah.
Because just one thickness.
Well, here is, you know, this number here, it's near the location, you remember, where there was the maximum volume flux. And look at how wide it is. So there are many thicknesses here.
Okay.
So this one is the laminar, this solid line is the laminar value. Okay, the thickness of the laminar value. And you see that when we are far from the wall, they are good agreement.
X, it's a normal, it's not normal, it's normal coordinate. X.
X, where is X?
X here.
Ah!
What does it mean?
No, okay.
I don't understand.
So, these are the measuring points, okay? So, you see that at these values of x plus, the flame is far from the wall. And while at this situation, the flame is very close to the wall. So, by doing this PDF, actually you can see that when the flame is away from the wall, it has a thickness that is comparable with the laminar flame. While when it comes close to the wall, it increases. You see why? I mean, this is the PDF of the gradient of C. So the higher the gradient, the thinner the flame. So for low gradient, here is low gradient, so thick flames. And here is high gradient, thin flames.
And viscous thickness is how much? Viscous thickness in comparison with
Viscous thickness?
viscosity divided by dynamic velocity. You showed it before, but I forgot.
You mean well, the problem is this is a gradient. You cannot compare this with thickness.
Inverse thickness.
Okay.
we can compare. I can find some, I don't know, characteristic thickness and compare with dynamic thickness. I can do that.
Yes.
all the time.
But you see, this is the laminar
Yes,
thickness.
practically laminar.
Yes.
So I speak about this laminar.
For the
Really, because for me it's not clear if the turbulent scales are larger than laminar thickness, it's quite difficult to imagine the turbulence enter to the.
okay. Yes. Yeah, I agree.
So I would like to compare the.
Yes.
So, what not we started is what's the diffusivity and what's the velocity in this case?
Yes. I will have to look it up. I don't have it. No. Well. The velocity. What velocity? What?
The RMS velocity. Of course.
Okay. Well, okay. In this case,
Yes.
it's probably, let's see. It depends where also. No. Because in the center line you will have some fluctuation. Near the wall you will have okay,
You have
8 meters per second.
Okay.
And
What's the diffusivity? Microscopic.
for what? For the burn? For
Yeah, which one?
But it depends for hydrogen. We have to multiply
Yeah, but if you take
times
for
and
this
the
one.
temperature.
Yeah, but what is it? Unburn and unburn. What are the two values?
I don't remember. Really. I would be speculation. So,
No.
but I mean, you can make a plot of the landscape, how it changes from the center line, and I did in fact from the center line to the channel wall, and compare this
But you
with
will
this.
compare this.
No, yeah.
It would be interesting to compare.
Yeah.
Oh, that's in so, and now?
Also, I mean, these three, yeah, in a sense, this ratio, you see it grows. So this gives you how some length scale change going from the center line to the
But
wall.
this bump, you have a very large
Yeah.
increase.
What is it?
It's
What
strange.
is it?
It contradicts to introduction to the concept that the edge is connected to the flame. It's strange.
Yeah. I don't know what that bump is.
It's a contradiction.
So when you showed this PDF,
Yes.
that was this done at one particular cross section, or up or down? I mean, that would change, of course, if you do it at different positions. Yeah, here, for example, this part. If you show me here. Oh, these vertical lines are the different
Yeah. Location.
locations, but
So-
but the different curves are for different
Well,
distances
you know,
from the
because
wall, right?
the flame here will move back and forth, no?
Yes.
So
right.
we did the sampling on this position and for the progress variable
Yes.
0.7,
Uh-huh.
and we get that curve.
Yes.
So in a sense, we picked
Oh,
all the points
Ah.
that are on average
Uh-huh.
at this position
Yes.
and that are on the
Yes.
progress variable 0.7
Yes.
and did that PDF.
Yes.
So it's a kind of representation of the flame thickness in this position.
Yeah, yeah.
And then of this, and then of this, and the flame gets thicker
Yes.
as we move there.
Yes. And the values you had were on the order of 40 centimeter
Yes.
minus 1,
Yeah.
which would be maybe large or small compared to the inverse thickness. It's rather diffused already. Maybe you're under resolving even. Maybe it could be that you're already under resolving.
Under resolving what?
Undersampling maybe. Undersampling thickness. The peak. The peak would actually be much bigger. Much sharper.
No, I don't think so. I mean
No.
I think that the fact that this line here is actually from this. So this is a laminar case. There I have a thickness
Okay.
and or a gradient
Yes.
of this,
Yes.
and the fact that the first positions are very close to the laminar value are in fact a good sign, because we know that in the center line of the channel the flame will be nearly laminar. But then this happens. Jim, what is
I'm just a little confused. You say the brush is thickened.
Yes.
That we saw.
Yes.
But now, is this the time averaged value of the gradient of C? So, in other words, is this the thickness of the individual flamelets within the brush?
No, this is not within the brush. This is conditional on the progress variable
conditional.
only in this position. Okay. So it's not across the flame, but it's in one position of the flame.
But C is not the time averaged C bar.
No, it's instantaneous.
It is time averaged.
Yeah.
Oh.
Instantaneous.
Oh, instantaneous.
Yes. It's like with the beans, you know, you put into beans all these values and then you make this.
I'm just curious, so you give the very strong vortices.
Yes.
Are you arguing they actually get within the reaction zone and broaden the reaction zone? Or is
Well,
it just spreading
this is my question mark. I see that the flame, I mean, this picture tells me, to me, I don't know what you think, this picture tells me that the thing gets broad, it's broadening, but what does this, I'm not sure. If it is small vortices that then train the flame and make it larger, or if it is a mere thermal effect, the fact that we have heat loss, and then the flame broadens. I'm not sure.
Unless you do an adiabatic flux simulation.
Yeah,
Really
yeah.
fast.
So to cut the heat, the heat flux.
It could be an effect that you have basically a quenching in that reason.
Yes.
Your quenching distance, and then your surface is parallel to the wall. Your reaction surface, and if you count that as a thickness, depending on how you calculate this, the gradient C.
Well, the gradient of C at C.7.
But there you have a parallel flame.
You know, C is not parallel. Look at this.
Okay.
Where is it? Well, this black line, for example. Look, this is C 0.7, the dashed line, and you see it's not parallel. It actually does like this. And here too, you see? Well, because C is defined that when C becomes larger here, then more has reacted. And probably, I mean, it is, more has reacted here.
Where you show the low scales going up and down.
Yeah.
You see the average flame position in terms of one class.
This one?
Yeah. If you want to draw a vertical line corresponding to the flame position, where would that be?
I'm not sure. I mean, this is only for this.
That's fine. If you want to draw a vertical line corresponding to the location of the basis of it, where would that be?
Well, this is the wall distance, so the flame is everywhere here, no? I mean, I am on the flame surface. This curve is on the flame surface. Or I start at C.1,
Right, okay.
0.5 and 0.7. So I am on the flame surface. Everything is flame here.
The main heat release is very good in this cold limits. Where we can place heat release.
The heat release is the maximum value of the heat release is nearly correlated with this. Yes. So it's everywhere. The maximum heat release is everywhere here. Yeah. Yes.
But my idea is this place is determined.
So, water. I can show you.
Many times it's not it's only a consumption speed.
All time is here. So he can't
Consumption
because the
is kind of global.
Massive mass that's being consumed. Except if you create an experiment that is designed to displacement. Robert Chang experiment that we had almost 5 turbines.
But even that is not significant. You have to know the velocity and some of these progress variables.
Right. And I think you found this. It wasn't as flat as you thought it was, and the flow was out of the turning on. It's all accommodated some there's argument for its own time. Most of them are long. That's right. The work that Janet statistically, there's a lot of scatter. There's a lot of uncertainty.
Okay, are you
Fundamentally, what she computes and what people can measure are two totally different things. Just takes the overseer's formula. All constants together equation, but then she has all sorts of gradients.
But that's extremely rough to make measurements.
You don't have all those terms that you can measure. So you know, at displacement speed, you typically
I agree with you, but not very
the speed of the wave. Relative velocity and displacement speed. You have to do it in 3 dimensions. That's the problem.
And what you
Okay, but
it's how you put your fingers
But if it's turbulence, that's the problem. If it's turbulence, it's normal is changing and, you know,
Even you can be situation.
all right, because we are just
we almost need to DNS working against the advanced concept.
what do you have to work
The way I look at it, the experiments are probably really just to provide some reality to DNS. But really, all this kind of advanced information will actually be someday. Not yet.
yes, you need this information.
Oh, yeah.
We're going to do this.
I don't think LAS will eventually be getting most of its information from DNS. But DNS will probably be validated, just because, like you said, the chemistry and bonding conditions.
It's very hard to write
The intellect
because
is
Yeah, yeah. But,
No,
this is correct.
very funny in these regulations
I don't know if that's true because you can't go to the higher rental standards to make it
in principle,
very much so.
like you were saying, is the chemistry. How do we know when the chemistry is
But this
good
is
enough?
for
And there's other issues about the pressure field.
No, but we want to see so what's the critical temperature when we don't have
So the
any
development conditions has to be defined.
Oh, right, yeah.
That's the idea, to find this critical temperature.
I
remember for 900 times the waves was
Okay.
And X equals 0, it's not it's a turbulent orbit, but how do you get those conditions? Is that from some previous computation?
All right. But I mean, you didn't say that what that is
We save it on this.
started
Every
box.
7 liters. So we have this large pipe. And then we remove this place and we
So at X equals 0, you have these kind of structures that you usually come in. But they will be
because there is another way.
So it's a very
And then you
could use laminar to turbulent vessels.
No, because we start with project research, whatever survives we hold, and then we let it go.
That creates these enemies.
Well, it's
yeah, I know. So, for instance, 100. But yeah, so
you have to drive, and then
because the thing is that
the drive after time,
right. But I mean,
yeah, you see,
it will be fully
10 to minus 4.
at the end of the challenge, we take whatever it's at the end of the challenge.
10 to minus 4. This is the
Interaction and I do interaction. In terms of mass flow, in this case, it's the same mass flow. This flow going down, balanced. Yeah, and it's moving. Everything is
In the average sense, it's the same.
But
the
if you make this at some point, you will have it in English. At some point, you have to
So this will be
well, but the area, no, because the area,
No, it's not in here.
Yeah, I think
the initial the full mass flow.
Yes, of course, there are some.
the other says the average
right? Energy depends on the depends on the size. So that's the which huge way.
Well, but I understand what you're saying. Think of these turbulent eddies and these structures. Little round. And some of those, the mean flows can have some gradients. May not be necessarily what we call vortices. Yeah, the flame will. You just have a laminar flow, but then you just have to be unsteady. It's an unsteady terms then the flame will rinse. So
Within this group, several
yeah, but
bigger,
yes, but we take moving at high speeds. See the eddy in one frame, and then we see the eddy in the next frame. We see the eddy we know that we have not made an error. If the eddy was here and then it disappeared and then it came again, then we have a big problem. But if you see the eddy in every frame as it moves along, then you know that yes, there really isn't anything. Because these are all the same.
the average is said to be bound.
But
you can have this kind
so,
of
but it's true that the error in the vorticity is more than twice the intensity. That's why it depends on the experiment.
because it's
couple of years to do this. Learn hard way. Some people say, well, why don't you just do this in a gas turbine? Or why don't you just in a scramjet? It's 5 years to do this once. So it's easy. Yeah.
Just different directions.
You know, one of our biggest problems is that if we have a closed experiment with windows, then the particles get on the windows. And it's a big problem. They probably have some enclosed experiment windows.
The problem is that you have a larger velocity difference. Somewhere you very large objects, and somewhere have low.
That's a dynamic range problem, yeah.
Then they cannot just at the same time have both.
Exactly. This experiment has has a very low dynamic range because the uniform flow, no boundary.
Maybe
So this was
I mean,
60.
don't worry about that. No, we have another experiment where we're doing a supersonic flow. And there you have a boundary on the wall. So accurate because you have supersonic like 700 meters a second.
So I have
You always have to make the measurement 2 or 3 times. You have to measure just the supersonic region. Then you measure the intermediate velocity. Then you measure the low because the instrument doesn't have a very large dynamic range. It takes years to do it. Many people don't appreciate it.
We're trying to do something for the and they only have 2 weeks to do it.
Were those measurements done here?
I mean,
Seems also the simpler, the smaller the extreme will be, the better quality.
Yeah, that's it. When we talk to computational people to try to get experiments to compare to models,
we're not dirty, but
I think we have to start small.
Yes,
Start small. It's just, and then you know, we also have to do almost the experiment twice. Because the first time we do the experiment, no matter how careful we try to be, we generally something's wrong.
if you take,
Like you were saying, the dynamic range may not be right, or conditions are not right, and then we learn. If we do the experiment a second time, then we know what to be careful.
It's really to hear because we collaborate. I do see,
this is the reactive.
and we often complain we have to do more.
Well, we're working with General Electric. You know, the first slide I showed you, the gas turbine, and it's they require that we use liquid fuel, which is a major problem with the experiment. And we've done Cliff, we've done formaldehyde.
This is the order of.
It's OH, but you know, the liquid fuel is so bright, it's so it's much worse than the gaseous fuels.
This is around 10.
Yeah, that's right. It's only a small region, but and it's very quickly turns into gaseous, but it's high pressure. So all these you look at it, they're so bright, you know, and you cannot do experiments with this.
yeah, it's correct.
pH.
It's correct. 10 times more you have to.
The only diagnostic we were able to use
So your
fluorescence was
but you know with high
then it's difficult to interpret it because
if you look at the temperature,
It's a good indicator of heat. It smells quickly at high temperature.
so these
They talk about
hydrogen, yes.
way G equation.
So these
The way you cannot
These one. So you have
you know, if you're studying a premixed flame, by definition, it's a wave that will propagate in a certain speed. It must be a functional mixture, right? So if it's highly non-uniform,
divided by
let's say between an equivalence ratio of 0.5 and 2, let's say it's flat, then you have a premixed plane that propagates in a wave. But
but I mean,
there will be other regions where
all this stuff here
it's
is
either too rich or too little, and you might have
so that's why
in the rich regions you might have a diffusion plane. So what I'm saying is the model has to
The system.
Yeah,
No, I mean is that's
cannot
very,
just
very
treat
thick.
combustion.
Yeah, so half a
combustion
millimeter is very thick for the
statistics.
reaction.
No.
Usually,
You know, in fact, I was saying maybe some of Steve Polk's models.
is around
I don't know.
half the
PDF?
PDF model. I mean, they seem to be very good for non-premixed planes. When you go to premixed planes,
I don't know if you
you just have to be careful. It's not an ensemble of particles that act in a statistical way. It's a wave.
I mean, you have much more.
It has a certain wave speed.
Propagating dynamically.
Right. And even the flame surface density wave in the wall. I'm not sure if you captures wave phenomena. The G equation does, because the G equation by definition is an interface that propagates normal. So I kind of like the G equation model.
If you have a local flame pulse,
but I was saying that
No, but you get from
You have a local flame up?
flame extinction.
Oh, yes, yeah, that is, yeah.
And also, if you have all ignition merge, all ignition flame propagation.
Well, you don't have the level set where it goes from 0 to 1 in reactiveness.
You have intermediate reaction rate. That auto-ignition problem failed, maybe it's very fast.
That's right. But maybe we'll have maybe Swami will talk or
okay.
Such Bennett has done some work on this. Is he going to talk about the physics also? Okay, good. Good. So he can talk about it. But you know, I think the problem is that some people are only doing modeling for a very small
That's pretty far from
type
the
of
wall.
problem. If you ask the foreman, you can just say, well, let's just model a flame that does not extinguish and is fully premixed.
Right.
So maybe a bigger question is, where is this all leading? How are we ever going to do the gas turbine type flames that we're interested in? Where we have partial premixed,
Or is it the inverse?
walls and all this.
Badly because you have
Another problem for
I think it's
badly because you have enough
I don't think
because you have
so it has nothing to do with the boundary.
no, because
value of the settings. And then how do you propagate these? Because you don't define the outside of it.
No, because you have badly
But I mean, if there is a number of breakpoints
you
or
have
something,
gradients involved.
and if that number is too large, then you can say that the private position has no effect.
Yeah, I've always wondered about
If
that.
this is like zero or something, I mean, honestly. How would
The way I'm familiar with the differential equation is that if you want to know the gradient, you have to define the boundary conditions. Because the G would have to be defined in all boundaries. If G was a state variable, then you would put values of G everywhere, you get the gradients. Well, you know, probably, but if G is not defined everywhere, then how do you get the gradient?
what people try to do is to impose another equation, not the T
You're very
equation.
close to the wall.
Not the T equation, but the equation for the distance. Basically, whether the T absolute value is greater than 1. And that equation do not need a boundary condition. In fact, you need a boundary condition to C equals 0 plus the boundary condition. And then you just go away from that.
Maybe it's
This way, but they never, there's mismatch between these two functions. Because one is another type, this is another one. And there is discontinuity at the maximum. So, I think that's the main reason.